Here we have a question where we have a 150-gram baseball is thrown at a speed of 20 meters per second, is hit straight back towards the pitcher at a speed of 40 meters per second. The interaction force between the ball and the bat is shown in the figure below. We have the force given as a function of time. What maximum force does the ball exert on the bat? And what is the average force that the average force of the bat on the ball? We can see that the force is given to us as a positive value, which from our convention means that the force is being directed to the right. If we know that the ball is initially thrown to the batter at 20 meters per second and it is hit away at 40 meters per second, that tells us that the initial velocity must be to the left so that the bat can apply a force, and then there would be a final velocity to the right. That tells us that the initial velocity will be negative because it's to the left, the final velocity will be positive, and then similarly the final momentum will be positive, the initial momentum will be negative. This is what we just determined, that the ball is initially at 20 meters per second. That's the speed, that doesn't tell us the direction. We decided that the velocity has to be negative 20 meters per second. It has to be going to the left so that there can be a positive force, and then afterwards there's a positive velocity, a velocity of positive 40 meters per second as the ball goes back outward from the batter and it's headed to the right. What this is telling us then, if we want to use a momentum bar chart, is that initially there is some negative momentum because our object is moving to the left at 20 meters per second. Finally, the object is moving to the right at 40 meters per second, so it has to be above the zero line in the middle. And we see here that the momentum should be twice as big afterwards than before, because if the object is moving at 40 meters per second, that's twice as fast as the 20 meters per second it began with. From this we can tell if we're down -1 and we end up as up 2, that means that the total impulse that we must feel must be a positive amount, must be a +3. And in this case, this impulse corresponds with the force that we're feeling. Basically, it corresponds with this area under the force versus time curve. When we wish to find the actual maximum force of the ball, we want to find the maximum force of the ball. We know the speeds and the mass, so we know about the momentum. The way that we relate the momentum of the ball to the force being applied is looking at the force as a part of the impulse. And so we'll look at the momentum and we'll look at the impulse to find the force. The change in momentum will be the final momentum minus the initial momentum, and that will equal this integral of the force. The final momentum is the 150 grams, written in terms of kilograms to be in the right units, times a positive 40 meters per second, minus the initial momentum times a negative 20 meters per second. And so what that gives us is a total of 9 kilogram meters per second is our total change in momentum, the total impulse delivered to our baseball. Now, if we want to know the maximum value of the force, we have to consider this whole area under the curve. We want to find the integral, but instead of finding the integral, what we're going to do is calculate this as the area under the curve. And we can do that geometrically because this is a triangle. And so this impulse is being delivered as a triangle. And so the area under that curve is 1/2 times the base, which is 3 milliseconds, times the height, which is F max. If we divide the 1/2 over, and we divide the 3 milliseconds over, we find that the maximum force is 6,000 newtons, or 6 kilonewtons. We can also find the average force of the bat acting on the ball. When we find an average force, what we're doing is taking this total area, but instead of having it be the area of a triangle, we imagine the same amount of area and thus the same amount of impulse, change in momentum, but we think about it as a rectangle. And so there would be a average amount of the force that would give you the same overall impulse, but just as a rectangle rather than whatever actual shape we're looking at. In that situation, the change in momentum would be the average value of the force times the change in time. Since the average value of force is a constant value, there's no need for an integral in this situation. We found that the change in momentum is the impulse. We calculated that to be 9 kilogram meters per second. And we know that the change in time is 3 milliseconds. Looking at the graph, the width of the curve, and thus the average value of the force is 3,000 newtons, or 3 kilonewtons.